Alright, hey guys, what's going on? So today we're going to be talking about labeling SU2 representations. So this is going to be at the core of how we sort of label the representations. It's sort of a mathematical, sort of technical thing to understand because everything going forward from here is not going to too heavily rely on this, but it's something that I think is necessary to go over. Just to have in the back of our minds, because a lot of the nomenclature comes from these types of labelings, and we're going to go into the background behind why all of this happens, why all of this labeling is the way it is. But anyways, let's get right into the content. But before we do that, make sure to hit that like and subscribe button. Again, if you're into this kind of content, this type of material is being posted is being posted on my Patreon page for those of you who are into wanting to get to this content earlier. So with that being said, let's get right into the content. All right, so we are going over the labeling SU2 representations today. So the way we're going to do this is we're going to start off by talking about our representations, right? So we talked about our J1, right? So I have J1 labeled here. Right here, right? These are just our generators, right? So, what we want to do is we want to kind of generalize things, right? So, we're talking about these being generators in a very sort of general sense. And so, what we're going to do is we're going to take our three generators. We're not going to really mention right now that they are SU2 generators. Okay, we're just going to say we're going to define this generator here, the square of this generator, as being the sum of all the generators that we have. Okay, and there's three of them. And so we can then, what we're going to do then is we're going to define, so this should be a matter of definition actually. So we'll put three equality signs there. So these are a matter of definition. What we're going to see is that these definitions are going to be really useful and really helpful in helping us label representations. So we're going to define these two guys here, this J plus and this J minus, as sums, as complex numbers, basically complex sums of these two independent generators, right? We don't have J3 in here, and we'll see why. J3 is going to help us raise and lower things. So we're just going to use the first two generators. This is somewhat of an arbitrary choice, right? We could use J2 to raise and lower things. We could use J1 to raise and lower things. The mathematics is still going to play out the same. We just, for our sake, we're isolating J3 here, and we're going to use it to calculate a few things. And so let's calculate this guy right here, right? So this is the commutator between the third generator, right? So the generator labeled with a 3 and J plus, right? So this is what that commutation relationship looks like. So we can substitute J plus in for these two guys here, and we do the mathematics, and when we do the mathematics we get J3, J1, J1, J3, so that's going to be this commutation relationship. And then I times J3, J2, J2, J3, right? So that's this commutation relationship right here. And then we are going to we know the commutation relationship already. We established this in the last video. This is just this, and this here is just this right here. Okay, so the I now gets placed on the 2 because these two guys got I times I is -1. Okay, and then because of this epsilon, that switches the sign again because we're going 3, 2, 1 instead of 1, 2, 3. So we're going backwards there, and we get this. And then from here we find is the definition of J plus, right? So we found that J3, the commutation relationship between J3 and J plus. I'll just write that down here. J3 and J plus is just J plus, right? So the eigen vector, if you will, for this commutation relationship, it just gives us back J plus. So we can do the same thing for J minus, and what we get is the general relationship that J3 commutated with any combination of our other two matrices, right? That's these two guys, or our other two generators, will give us this relationship. All right, so this is important. We'll see this come up in our Lorentz representations as well. We can also find, right, so you can actually do, again, the math isn't too hard. You can do this for yourself. We can find that J plus commutated with J minus is going to give us our J3. Okay. So, okay, we have that. These are all just, they seem like somewhat random relationships, but they're all going to help us with some further calculations. So we now invent state vectors that these matrices are going to act on. And these state vectors are going to have two input values to them, right? So one input value is going to be B, and the other one's going to be M. B is called a Casimir element. Casimir element operators will provide labels for different representations of our theory, if you will. And Cartan element operators, that's going to be M, that's a second entry in our state. It's going to provide labels within a given representation. So you take one representation, you say the 1/2 representation. We'll talk about what that is. Within that representation, there's different elements, right? And we want to be able to specify the representation and then narrow down which element within that representation we're talking about. So to do this, first we want to consider this. A lot of this seems arbitrary, but this is sort of what physicists do, right? They consider something that looks like this and they see what happens, right? So let's consider this. So we say J3, J plus, right, acting on BM plus all this. This is just adding 0, right? Because J plus minus 3, J plus minus 3, and there's a minus right here. You're adding 0. Right, so this doesn't do anything, but we can move this guy over, or we can move one of them over, right? So we move this guy, we basically swap these two guys. All right, so this guy is here, and this guy's here, and we get now this and this. Right, this is just commutation relationship, J3, J plus minus, J3. Commutation relationship, we found the commutation relationship was this guy right here. And then, so we get this guy here, right? Because we said J3 right here is a Cartan element operator. It'll bring out M. This is just by definition. Right, so if we say that J3 does that, and J plus minus, that kind of just stays the same, well, then we can bring an M out. We get M plus 1, and then J plus minus, and we have this BM right here. So we find that J3, when it acts on this state right here, this J plus minus and BM, that raises the eigenvalue by M plus 1. Okay, so this is an interesting relationship we want to keep in mind, right? And you can pause the video, you can go back, and so forth. But this is sort of leading us to the grand step here. So for a given value of B, we want to ask what is the most number of M's. So what's the most? How many elements are within a given representation? Basically, this will be important for when we label representations of Lorentz transformation later. So let's take a look at how we can answer this question. So to answer this question, we then consider an M max, right? And we say, let's take these two guys, right? So this is, what's this? This is J minus, and this is J plus, right? So if we look back here, right, so J minus and J plus, that's right here. So let's take a look. So what we want to do is we want to take a look at what this exactly looks like now. What happens when we do J minus J plus on B max, right? Because, and we'll see. So J1, right? So J1, that's going to be squared. We're going to have 2 parts of J2 squared, right? And then we're going to have, the reason that's going to be squared, right, because we have a minus I times I, and that's going to be -1, so that's going to come out to be positive, and our two J2s are going to be squared. Right, so those are those two guys. Then we have our commutation relationship, right, because we have J1, J2, J2, J1, right, so J1, J2, J2, J1, and then we have these I's coming out here. So if we come here now, so we have this, we want to get now, so this here, we found, if we recall from up here, right, this was just a matter of a definition, right? We say these two guys is just this minus this, okay? Right here, this is, again, a commutation relationship for our SU2. This is our Lie algebra for our SU2. So we get, here's this guy, and then I, J3, but this I again times this I. All right, so that's going to give us a minus sign. Okay, so we get this, oops. So we get this guy right here on our state vector. And so now, okay, so if we go back to our definitions, we said J3 brought out M, and J squared brought out B. And we'll recall the names of these guys, right? So this is the Casimir element operator, and this is the Cartan element operator. And so here we have B, so J squared taking out B. J3, right? So J3 is going to bring out M, and we're bringing out M max, right? Because that's what M is right here. M right here. So, and that's going to be squared because J3 is squared, and then we're going to have another M max J3 is bringing out. Okay? So now, what we are doing is we want to set this equal to 0, right? Because when J plus acts on J max, well, we shouldn't get anything more, right? We're acting on the maximum value for M max, so anything beyond that is just nothing. So we get this guy here equaling 0, right? So what does this mean? So we set all this equal to 0. We find that B equals M max times M max plus 1. Similarly, we do this, right? We swap plus and minus, and we'll get some, you can do this for yourself, but B is going to equal the negative of M min times M min plus 1. Okay? So comparing these two equations now, if we set B equal to B, which we can do, we see that M min is the negative of M max. And so to put this sort of into a picture perspective, B is going to label our representation, right? So this is our representation, and these guys are the elements in the representation. Again, these things are brought out by Cartan. Make sure I get these right. So Casimir element operators, Casimir and Cartan element operators. We're getting this is within a given representation, right? Given representation, we have a maximum number of elements and a minimum number of elements, and the max is equal to, or the min is equal to the negative of the max, which is what we found. So if we set the difference between these two to be a constant, we say M max minus M min is a constant. Well, if M min is the negative of M max, then 2 times M max is going to be the constant. Okay? Therefore, M max is the constant divided by 2. So if we set this constant equal to 0, say, then M max is just 0. So if we set it equal to 1, though, right, it's going to be 1 divided by 2. It's going to be 1/2. Right, so if we set that equal to 2, or 1, then our m max is going to be 1/2, and our m min is going to be minus 1/2. Right, so for m, so we can do m plus 1s, right? So the only two values we get then are 1/2 and negative 1/2, right? Because the difference is an m plus 1 difference, because what we found that over here, actually. We found it right here, right? There's an m plus 1 difference between the elements within the representation. Okay. If we set our constant equal to 2, well, that sort of expands. You could think of that as sort of expanding the difference between m max and m min. And so m max is going to be 1. M min is going to be negative 1. Right? And so we get 1, 0, and negative 1. Okay. We can do the same thing for 3, and we can keep on going down this line of reasoning. And so this dimension column I have here. So this dimension column says, well, there's one number we have here, and that's 0. So this is a one-dimensional representation of our of our SU. This is a one-dimensional representation of our transformation. Right. So for a two-dimensional representation, we have two values, 1/2 and negative 1. Right. For a three-dimensional, right, we have 1, 0, negative 1. Four-dimensional, and so forth, right? 1, 2, 3, 4 dimensions, right? So we can sort of talk about now a four-dimensional representation of, say, a Lorentz transformation. We can sort of understand what that means now. The number of dimensions refers to the number of elements within that representation. So we can talk about, say, for example, this is how we're going to label representations of the Lorentz transformation, right? So we're going to have 1/2 0 representation. So we can sort of make sense of what this means now, right? So the 1/2 refers to the dimensional representation, so this 1/2 refers to this 1/2 right here, essentially. This 0 refers to this 0 right here. Again, 0 refers to this 0 here, and this 1/2 refers to this 1/2. All right. So what we're going to find for Lorentz transformations is that a representation, when we say, or when you read things like a 1/2 0 representation, this representation is going to act on left chiral spinors. Right. So this is a representation of the Lorentz transformation. We're going to talk exactly what the Lorentz transformation is, but this is a representation of that transformation, and that representation, because it's only two-dimensional, is going to act on objects that only have two inputs on them. There are vectors that essentially have two inputs on them, and those two things are chiral spinors, right? So, because the spinors, again, they can be up or down, right? They only have two dimensions to them. Similarly, the 0, 1/2 representation is going to act on right chiral spinors. And then we're going to have the 1/2, 1/2 representation. And what we're going to find there is that they are going to be the things that act on four vectors. And more precisely, these guys, I'm realizing right now this is a little small, so I'll blow it up. But these guys, what we're going to realize is that they are actually combinations of these two representations here, right? And so a sort of notation that you'll come across is a notation that looks like this, where there's essentially an equality sign right here not between the 4 vectors, but here, I'll write it like this. I'll move this guy down here. I'll draw an arrow. But this 1/2 representation, this 1/2 representation is the same thing as saying we take the left chiral spinors and the right chiral spinors, combine them together, and we'll find out that that combination gives another representation. That representation acts on the 4 vectors, right? And you might think then is there a way to represent 4 vectors in spinor form? And the answer to that is yes. And we're going to see exactly how that's going to work out. And that's also going to give us some insight as to how we might inch forward to a grand unified theory, how exactly we could unify vectors with spinors and see exactly, we'll see that one is sort of a lower dimensional representation of the other. That's one way of thinking about it. But anyways, if you like this kind of content, make sure to hit that like and subscribe button. And also, if you're hanging on through these videos, I have mentioned before that these videos are going to be going up early on my Patreon account. And you could stay on top of that if that's something you're interested in also. So with that being said, I'll see you guys in the next video.